In this video, we're going to talk about exponential functions, and we're going to review how to use formulas for compound interest and continuous interest to help us solve application problems. But before we do that, let's talk about the number e. So e is an irrational number, really similar to pi in that respect. It's one of those that never repeats and it never ends. And the definition for e is actually based around this idea of a limit. So let's look at that. So e is equal to the limit as n goes to infinity of this expression, 1 plus 1 over n to the nth. So I'm going to graph that in the calculator so you can see what that's approaching. I'm going to go with a standard window. So we are going to look at what happens as n goes to infinity, which means we're looking at this right-hand side. And I'm going to go to my table. So as we type in numbers that get larger and larger and larger, look at what's happening to those y's. They're actually approaching a very specific number. That number is what we call e. So you can see over here, we started at 2.7048, and then we progressed pretty much to 2.718. So then when we type e in our calculator to get a decimal representation, that's what the calculator is doing. It's finding that limit as n goes to infinity of 1 plus 1 over n to the nth power, and that's the number that results from that limit. Now, we could actually rewrite this way just by doing a simple substitution. If we let s be equal to 1 over n. So now we have a substitution here. So now we've got that 1 plus s. We could solve this for n by multiplying both sides by n and then dividing by s. So now we have a substitution for the n here. We just need to figure out what's happening with that limit. So if you think about what happens as n goes to infinity, this is going to tell us where s would have to go. So as n gets larger and larger and larger and larger, then this whole fraction is getting smaller and smaller and smaller, which means it's approaching 0. So s is going to have to head to 0 there. So just making those simple substitutions gives us a definition that is equivalent to what we started with. All right, so let's review the interest formulas. We have 3 that we can talk about: simple interest, compound interest, and continuous interest. Simple interest is interest that happens one time. So your future amount A is equal to P times 1 plus RT. P is your principal. That's the initial amount that you're investing. R is your interest rate. It has to be written as a decimal. And then T is time. So with compound interest, it's a little different. Simple interest is one time on the life of the loan, period. Compound interest means you're getting interest upon interest. This is what your bank account does. So if we were to take money and invest it in a bank account, some bank accounts earn like 3% interest over the year. So you're going to get part of that interest compounded. Most banks do every month. So then you'll get interest on the first month. And then the second month, you'll get interest on how much you invested, plus interest on the interest that you earned from the first month. So it's compounding, which means that you're getting interest on that interest. The formula is a little bit different. It's P times 1 plus R over N to the NT. N represents the number of compounding periods per year. And then there's continuous interest. If we were to take the limit as n goes to infinity of the compound interest formula, we will get the continuous interest formula. And what that means is those compounding periods are getting smaller and smaller, or, well, they're getting larger and larger, so that you're compounding closer and closer and closer and closer together. So what's happening is this ends up approaching E. So let's talk about how we're going to use the formulas. In the first one, what amount will be in an account after 5 years if $100 is invested at an annual rate of 8% compounded annually? So notice they're using compounded annually. That tells us we're going to use first the compound formula. And then we're going to redo it with semi and then continuous annually. Semi-annually and continuously. So what information do we have? Well, we know the initial amount is $100. We know the interest rate is 8%, which is 0.08 as a decimal. And then we're going to leave it in there for 5 years, which is T. So annually, we're going to have A equals P, 1 plus the interest rate divided by N. Now, since we're doing this annually, N is 1. To the 1 N times T. T is 5. Before you type this in the calculator, you're going to want to simplify that exponent there. It's just going to make it easier. So now when I type this in the calculator, I got about 146 and some change. Since it says round to the nearest cent, that would be 2 decimal places. Now let's look at semi-annually. Semi-annually means twice a year. So A equals P, 1 plus the rate divided by N to the NT. Let's simplify. 0.08 divided by 2 is 0.04. And that's going to be raised to the 10th power. Type it in our calculator. I got 148.02. And then let's look at continuously. That's where we're using, I like to call it the PERT formula. Principal is 100. Interest rate is 0.08. Time is 5. I like to simplify the exponent. And I got 149.18 for that. So you can see here, you can kind of see the compounding periods getting closer together here. If we were to do quarterly, monthly, and then daily, you would see us approaching that continuous interest amount. Just for fun, let's do that. Let's look at quarterly. Quarterly would be 4 times a year. So we're going to be at 148.59 monthly. Monthly is 12 times a year. Now, 0.08 divided by 12 is not going to reduce very nicely, so I'm just going to leave it like that. But I can still reduce that exponent. I've got 148.98. And then just for fun, let's do daily. There are 365 days in a year. So I'm just going to put a few more decimals out here so we can do a comparison a little bit better. And I'm going to go back up to our PERT formula, and I'm going to do a few more decimals there so we can do a comparison. All right. So here's what continuous interest does. As the compounding periods get closer and closer together so that you're compounding more frequently, then that compound interest really is approaching that continuous interest. And you can see that here. So we started with annually. And if we compound one time a year, we ended up with 146.93. So now, in semi-annually, instead of compounding once a year, we're compounding twice a year. And we've increased our amount here. We're now at 148.02. If we look at quarterly, we've now increased to 148.59. So we went from one time a year to 2 times a year to 4 times a year. Now let's do 12 times a year. So you can see how I'm starting to kind of flatten out that amount. I'm at 148.98. And then if we look at daily, we are at 149.18 if we round to the nearest cent. So let's compare that value to our continuous interest value. You see how they do round to the same place if we look at the nearest cent. But if we expand those decimals just a little bit, you can see how that daily amount is getting really close to that continuous amount. And that's what's going to happen with interest. So let's look at another problem. In problem 2, we have 5,000 that's invested. And it's earning a rate of 5.61%. It's compounded continuously. We want to graph this function for a period of 4 years. So since we're using continuous interest, we're using the continuous interest formula. And we're going to graph this with respect to time. Our P is 5,000. Interest rate is 0.0561. And looking at it with respect to time, T. So if we wanted to graph that, so I'm typing in 5,000 e to the RT. And I'm going to use X for T here. Okay, now keep in mind that initial amount that we invested was 5,000, so we're definitely going to have to adjust our window. I'm just going to go from 0 to 4 since this loan is, the CD is a 4-year CD, and we're graphing it for a period of 4 years. And then we're starting at 5,000, right? That's our initial amount that we're investing. So I'm just going to go just a little bit below that, 4,500, so we can see the full graph. And let's try 6,500 and see if we can see everything going up by 500s. Graph. So I'm just going to hit trace. So if we go back to 0, you can see there's my initial amount I invested. And if I want to know how much I invested, how much I have in the account at 1, how much is it worth? That would be 1 year into it. It would be worth $5,288.52. And if I want to know what it is at 4 years, and I'm literally just typing the number 4 in, it would be worth $6,257.86. So you can see how that amount is changing. Look how much interest we earned. We started at 5,000, and 4 years later we're at $6,257.86. So we have earned quite a bit of interest here. If we subtract those two numbers, 6257.86 minus 5,000, we've earned over $1,200 in interest. And that comes just from the power of compounding here. We didn't do anything special. We put this money into this CD and we just left it alone for 5 years, for 4 years. And that's how much we earn in interest over that 4-year period. Let's look at another problem. How long is it going to take to double, for money to double, if it's invested at 5% compounded continuously? So we don't have an initial amount here, but we know we're compounding continuously. So let's say we invest P. Then after some amount of time, we're going to double that amount to 2P. And we want to know how long it's going to take. Our interest rate is 5%. We're looking for time. So we need to solve this equation for T. Our first step is to divide both sides by P. So we're going to have 2 equals e to the 0.05t. And then we can take the ln of both sides. So we have the ln of 2 is equal to 0.05t. The right hand side uses log properties to simplify. Divide by 0.05. So t is equal to the ln of 2 divided by 0.05. And we're going to want a decimal approximation for that. This is one of the few times where you'll be asked for a decimal approximation. And it looks like it's going to be about 13 years. So it's going to take about 13 years for any amount to double. It doesn't matter whether I invest $1 or I invest $1 million. It will take 13.86 years for that amount to double. And then if we look at problem 3, how long will it take for an investment of $1,000 or $10,000 to grow to $15,000 if it's invested at 9% compounded continuously? So in this one, they're giving us two amounts. That future amount is $15,000. The current amount is $10,000. Interest rate is 0.09. And once again, we're looking for t. We're also using that continuous interest formula. So let's divide both sides by 10,000. Take the ln of both sides. So we're going to have the ln of 1.5 is equal to 0.09t divided by 0.09. And once again, we're going to want a decimal for that. And it looks like it's going to be about 4.5 years. And then if we look at problem 4, we're considering 3 options for investing $10,000. We've got an annual option, a monthly option, and a compounded continuously option. Notice the interest rates are different. We're asking which option is going to be our best investment in Part A. So let's look at annually. So for compounding annually, we're using that compounding formula. We are investing, let me write it this way, 10,000. Interest rate is going to be 7%. We're compounding 1 time a year. And we're doing this for 8 years. So if we type that in, we're going to get $17,181.86. It's like, okay, that's pretty good. But what happens if we change the compounding period and the interest rate? Is that going to be a better deal? Let's see. 10,000 invested at 6% compounded monthly for 8 years. So I've got 16,141 and 43 cents. So as of right now, that's not better than the annual amount. It's actually less. So let's look at the continuous amount. That would be getting interest on every second of every day it's in the account. Now, continuous formula is the PERT formula. So we're investing 10,000. Interest rate now has changed to 5%. And we're still doing 8 years. And I ended up with $14,918.25. So if we look at these 3 options, which one is our best option? Well, it turns out that the first one, the annual one, was actually the best option because it gave us the most money after 8 years. And in this case, this one ended up being the worst option because it gave us the least amount of money after 8 years. So let's look at the graph so we can answer part B. How long would we need to invest our money for the third option to actually be the best option? So we're going to graph these equations with respect to time for the annually one. We're going to have A is equal to 10,000 times 1.07 to the t. We can graph the monthly one too. And then the continuous. So we're going to plug those into our Y1, Y2, Y3. Y1 is the annual interest formula. Y2 is monthly and Y3 is continuously. And we're going to have to change our window again. So I'm going to go from 0 to 100 just so I can get a good idea of what this graph looks like. Remember, we're asking how long is it going to take for the third option, which is the continuous option, to be the best option. So we're looking for where that's going to outgrow the other two. So I'm going to go from 0 to 100, and I'm going to go up with a scale of 10. My Y's, I'm going to go from 0 to 1 million and go up by 10,000. Now let's go by 100,000. Let's see if that gives us a good graph. So there's the first one. Remember, that was the annual. There's our monthly. And then finally the continuous graph. So if you look at these three graphs, there's never going to be a time where that continuous interest is going to outweigh the other ones. So it's not going to be the best option. If you look at where my pointer is here, if I look at this moment in time, whatever that x value is, the first graph here, which is that annual graph, is going to have a bigger y value than the other two, and the y value represents the amount that's coming out here. So that amount is always going to be larger based on this information, 7% compounded annually, than both the monthly, 6% compounded monthly, and the 5% compounded continuously. So the answer is never in this case. We can also see that if we look at the table. Let's say we wait 5 years. There's our amount after 5 years for the annual, monthly, and continuous. If we go 10 years, you can see the annual amount is more. 15, same thing. And it doesn't matter how far we go, that continuous interest is really just gonna kind of lag behind here. We're at 38,000 versus 33,000 versus 27,000. So there's almost a $10,000 difference there. Now, it would be a different scenario if those interest rates were the same. Then the continuous interest would be more. But because that interest rate changed so much for the continuous interest versus the annual, it ended up not being the best option here.